So recently we had the meetings where we have colleagues from China and from Stanford. So this was kind of hard to get the right time. So it was every time bad for someone.
Yeah, I think we've had to do that too. I think it's a 12-hour difference between Texas and Beijing.
Right.
Makes it hard.
Scott is connected from plane.
That's what it sounded like. That better?
So Chuck, are you going to share the slides afterwards somewhere? Or is it just a live demo?
Well, we're recording this. I guess
okay, good.
the destination is going to be YouTube for that. The slides are in PDF form. I'm happy to share them, but I'm not sure where would be an appropriate place. Maybe nfsv4bat.org, or I don't know. Is there a file repository associated with the Discord servers? If so, then we could use that.
Yeah, I plan to do the nfsv4bat.org, and
Okay, so
Chuck, if you'll send me materials, I can push those up there. I have the credentials to do it.
okay, thank you.
And,
Technical question was, should I capture somehow, or will be something available at the end?
So I'm gonna wait another few minutes here for people to collect. Since this is not a regular meeting, I'm sure people are going to be a little late.
I'm going to stay muted. Hello, all. I'm going to stay muted for a while. I'm at my daughter's apartment and they're packing. So I will be mostly on mute.
Does everyone hear that sound when anyone mutes? That's very annoying.
It's pretty old school.
Old school or not, it's annoying.
Probably someone who is not muted is feeding that back into their mic.
Hello, everyone.
Hey, I'm gonna wait a couple more minutes just because this is not a regular meeting, so people are likely going to be a little late.
Not a regular meeting, so it's an irregular meeting.
I'm resisting the urge to make comparisons to bowel movements, but right.
So did
Yeah.
you notice, Chuck? Bill have written down non-regular meeting.
I used Chuck's previous comment, a dog and pony show. That's what I put on my calendar. Dog and pony show. Does that make me the dog or the pony?
You can be whichever one you want to be.
You're first, so you must be dog and I'm pony.
We all love dogs here.
Maybe my dog will come in as a guest star.
Yeah, could be.
She's hiding somewhere. I don't know where she is.
I just noticed there does seem to be under settings there's a bunch of notification settings, and you can turn off the notification for mute, unmute. At least it works for me. I do this, and I hear nothing now.
What? Just kidding.
Which one? Message?
Let's see. User settings.
Yeah.
And then there's probably some sort of menu bar on the left. There's notifications. And then under notifications, there's a whole section for sounds. And there's mute and unmute.
Much better. Thank you.
All right, it's 5 after the
You're
hour.
welcome.
I think it's high time we get going here. I'm gonna walk through some slides to talk about what we're doing with Tracepoints and dprintk in the Linux client and server. I'm not really going to dive into what the stuff looks like in code, but I'm going to talk about the way I use them and when I troubleshoot. I want to give a kind of a flavor for why we're doing this, because it's pretty disruptive. I recognize that, but we think there's a lot of value in adopting Tracepoints as a mechanism that sort of is significantly better than dprintk in a lot of ways and can substitute for network capture often enough to be quite valuable. I mean, it doesn't always, but it really is something that a lot of subsystems in the kernel are adopting. So we think it's a future-looking mechanism for doing troubleshooting, especially for people in the field, not developers, but administrators and end users. So I'll dive right into it. The first and primary improvement over dprintk is that these things are a lot more efficient. They don't involve any I/O at all. A dprintk will involve a file I/O into the system log, and it will also involve a console log. console I/O, which goes at the speed of the console device. And in a lot of configuration, that device is very slow. It can be as slow as 9600 baud, which is very 1990s, but there it is. Some people just don't ever bother to increase that, and so that becomes a bottleneck when you're trying to observe activity that happens at a high rate of speed, which is common for NFS operations. The turning on Deep Print K can slow things down quite a bit. It changes timing. It fills the root file system. There are lots of bad things about it. So that's the main thing we really like about Tracepoints is, it's a memory only operation. Another thing is with Deep Print K, you set a flag and you get a whole ream of Deep Print Ks enabled at the same time. With a Tracepoint, you have pretty fine-grained control. You can enable one trace event. You can enable a small set of them. You can enable a whole subsystem. It really allows you to do very good culling of the events as you're doing the tracing. So you're not capturing a huge amount of data that you're going to have to filter later. You can capture exactly what you need. And there's a pretty sophisticated filtering mechanism, even if you do need to do that. If you're capturing a single trace event and you only need that to see that event in particular cases, you can trace while the capture is going on, or you can trace afterwards when you're dealing with capture data in a file. Tracepoints capture a lot of information by default, aside from the stuff that you specify for each particular tracepoint. A tracepoint in general capture a microsecond precision timestamp. It captures the CPU ID, process ID, the command that's running, interrupt state, that kind of thing. All that stuff is in every trace event by default. So the trace events we define in NFS and SunRPC get all of that in addition to whatever we define for that particular trace event. That's a lot of information that doesn't come with Deep Print K, for example. Deep Print K doesn't have a microsecond precision timestamp or CPU ID. It just sort of blathers out. It can have a timestamp that's of decent precision, but it doesn't include CPU ID and other things like that. And you can filter on these things. You can filter by PID, you can filter by CPU ID, etc. Another really nice thing about Tracepoints is they are nicely integrated with other observability mechanisms in the kernel, like kprobes and system tap. You can turn on multiple trace subsystems at once. So we've got a trace subsystem in NFS client and one in the NFS server. We've got them in the RPC components. We've got a trace subsystem for the RPC over RDMA transport, and they're all controlled independently of each other. We can enable them all at the same time so we can see activity across the stack. You can also turn on trace points for the scheduler, the kernel scheduler, or KMEM, or block devices, and all that stuff gets stuffed into the same trace log and interleaved. So you can actually see control flow pretty easily by looking at the timestamps. Tracepoints also have plugins, what are called plugins. So you can look at things like, you can ask it to do function boundary tracing, and that's a Solaris term, or I guess it's from dtrace, which it's just a fancy way of saying you get to see when you encounter the entry point for a function and the return. And you can control the depth of that. So say I want to turn on tracing at XPRT connect. And then you can say, okay, start tracing there, all the function calls up to 4 or 5 deep. And so you get to see just that little piece of the function graph as it's executing connects. That's pretty handy. The maximum graph depth is very important because if you don't specify that, the call stack can get pretty hairy and pretty deep, and so you can collect a lot of information that way, and even deadlock the system because it becomes an overwhelming amount of data. I'll show you a little bit more about that in a couple of slides, and in the demo that I'm going to do after we're done here. There is also a feature called I think, I don't remember it because I don't use it very often. So I just look on the man page when I need to use it. But when you hit a function, you can do a stack trace. So it's like inserting a warn on at every time you enter a particular function. You can have more than one of these things. So it's, you can figure out who's calling something. And all of it, as I said before, all of this gets sort of shoveled into the same trace log and timestamp, so you can see exactly what's going on. It's very, very, very valuable information. So for the trace events that we've been putting into the NFS stack, we've been trying to architect them a little bit. In addition to the stuff that comes with generic trace events. So they usually collect a common set of information. On the client side, you get to see a task ID, a PID, TK PID is the field. So the RPC task, the connection ID. On the NFS side, you get to see the NFSD PID. You see an XID in a lot of cases. You see endpoint addresses. That's an IP address of the remote that it's talking to. So we try to build those all in as part of the trace events that we're adding, or where we're replacing dprint keys. Because we want these things to work in cases where the client or server is running in a large installation. You want to be able to see, oh, who's doing this obnoxious thing to my server. And the trace event should show you an endpoint address and port. As often as we can, we get these trace events to display information symbolically. That is, you get to see NFS error blah instead of just a number. The trace pointing subsystem has facilities for doing this, and whenever I add a trace point, I always make an effort to add the little mapping in there so that it doesn't display the number, it displays an actual word that's human readable, and you don't have to go back and consult the source code to figure out, oh, what is that? What is -22 again? So that's in there. The raw data is still available. It's stored in the trace log, and you can use an option on the trace output so that you can see the raw data. So the numbers are available, but I usually find that the symbolic information is a lot more valuable, and so that's how I set up the trace events. Bill Baker has imparted some wisdom on us about how we can, in advance, keep the information flow as narrow and manageable as possible by reducing the amount of chattiness of these trace points. So we have these two broad categories of trace points when we add them. One is control flow, and that's sort of, I got to this point, I'm using this resource, or I made this decision, and I'll show you some examples of that kind of trace point. Those are very chatty, so when you enable them, you get a lot of information, and you have to weed through it. But if you're really unsure of what's actually going on, these are very important to see, because then you can quickly knock down alternatives and say, okay, that's not happening. I definitely see the control flow taking this particular path in the code. And then the second category is exceptional trace points. We've tried to name those trace points with a name that ends in _ERR, so they're easy to enable and quickly, and as a set or to identify them. And what these do is they fire only in the case of code that is exceptional. It's stuff that's not supposed to happen, I guess, or errors. So we have a set of trace points in the RPC client that call out program not registered, for example, when that's a bind result, an RPC bind result. And so there's a bloody-blod underscore error trace point in there that can be left on all the time and will only fire when you get these very rare program not registered events. So I'll give a little more demonstration of that when I show how to use the tools and run the live demo. So before I run the live demo, I just want to describe. Well, actually, let's back up. Are there any questions before I go on? Okay. So a lot of people who have been using this facility for a very long time tend to gravitate towards the sysfs files and they poke values into the sysfs files to get the dog to jump through the hoop. I did that for a while, and I didn't find it. I found it pretty cumbersome and not very reliable. And eventually, I discovered this trace command line tool, and so I've been using that pretty exclusively to control the trace subsystem and to display and filter the captured trace output. So what I'm going to do now is sort of give an overview of that command, what it can do, and then I'll move on into a demo of how I might use it in an everyday situation. So the first thing to know is how do I find out what are the trace events that are available for me to enable. So that's easy. You just do a trace command list. You usually need a sudo, or you need to do it as root because the sysfs files are locked down. So you can just type trace command list, and then it will give you a lengthy bit of output. I usually pipe it into a pager so that I can search it easily. And it will display the subsystem like RPC RDMA or NFS, a colon, and then the name of the event that you can enable or disable. You may notice when we go and do this that the NFS events, the NFS subsystem doesn't appear. It might not. And that's because trace events that are in modules that haven't been loaded yet will not show up in this list. So if you want to see the NFS events, you have to make sure that you've done a mod probe NFS or mod probe NFS4 first, so that those trace events are registered and trace command list can find them and show them to you. So enabling these things is pretty simple. Once you found a trace point or a subsystem that you want to enable, you just use trace command start -e and then the name. So if I want to enable all the trace points in SunRPC, I'd say trace command start -e SunRPC. And you can do that. You can repeat the -e multiple times to enable multiple subsets of these things. So I might do trace command start -e SunRPC -e NFS -e RPC RDMA. And then I'd get a whole set of information out when I do something. So trace command start is you just type it and hit return, and it comes back immediately, and it sets everything up in the sysfs, and tracing is started. You don't see any other information from this command. It just says either I did it or I couldn't find the trace points you asked for. Pretty straightforward. And so tracing is running at that point, and you can do things. You can run commands, you can mount whatever you want to do to reproduce your problem, and that will all be captured until you do a trace command stop. At that point, that shuts down the tracing, but it leaves the trace subsystem active. If you want, and at that point, the trace information is still in the kernel's trace buffers. So you can use commands I'm going to show you in a minute to look at the trace buffer and see what's in there, and until you do a trace command reset, and that turns all the tracing facility off. It leaves performance unchanged to a normal system, and it erases everything in the trace command in the trace buffer. So these are the three ways you get to enable and disable trace points.
Chuck, I had a question.
Yeah, go ahead.
Yeah, you can back up if you want. Does trace command offer any kind of globbing for trace points? You mentioned probes ending in under so could I say sun RPC : star under to trace command?
Theoretically, yes. I've never gotten past the sort of interaction between that and my shells globbing to get that to work right. I think you need a \star or something like that, but it's supposed to work. Yeah.
It's supposed to work. Okay.
Yeah. If you wanna try that out, y'all, all y'all. I'm not talking about you, Bill. If you want to try this out, then look in the man pages, or there's loads of information on the interwebs about how to do this stuff, and you might track something down that works for you. Any other questions while I'm stopped? Okay. So now that you've captured something in the kernel's trace buffers, how do you view that information or even extract it? There are two ways that you can do that. Trace command show will display what's in the trace buffer without consuming it, so it's left in there. You can do trace command show any number of times, and that doesn't change what's in the ring buffer as long as tracing stopped. So the ring buffers are limited in size, which means you turn on tracing and it basically will show you the last set of trace events that happened before the ring wrapped in it. That's pretty useful if you have a reproducer that runs and runs and then it crashes. As soon as it crashes, you can do a trace command stop, or it doesn't generate any more trace information at that point, and you can do trace command stop and then look in your buffer and you'll see the last trace events that happened. The other thing that you can do is look at the trace output pipe with -p. I haven't been real successful at this. I haven't quite figured it out yet. Sometimes it works for me, sometimes it doesn't. But anyway, in this case, you would do trace command start, and you specify your set of events that you want to enable, and then in another window you do trace command show -p, lowercase p, and that is it's like a tail -f on the trace output pipe, and it should display trace events as they happen. This is a consuming read, so as soon as the trace event comes out of this command, it will be taken out of the ring buffer, and so the ring buffer is emptied at that point. So I like to use this when I can. If I hit a crash or something like that, I can do a trace command show -p and watch it happen, and spills into my terminal buffer, and the system might crash eventually, but my terminal buffer I'm SSH'd into a server somewhere, so that terminal buffer has the trace events in it, and I can just examine them that way. Although generally I just like to use trace command show without the -p, because the ring buffer isn't consumed, it's all in there. You can use trace command show and pipe it into less or your favorite pager, and it doesn't change. You get to see the information and trace and filter it. Trace command show has a filtering facility. I'm not really going to go into a lot of details there, but you can have a look at the man page to see what's the man page. Trace command report is the man page that I believe walks you through how the filters work on this. Those are post capture filters. Now, if you want to capture trace activity over a long period of time, and you need to have the whole set of trace events, and you don't want to limit to the size of the trace buffer, you can use trace command record. It works like trace command start, except that once you type trace command record, if you don't give it a command to run at the end, it will just hang there and wait for you to Control C, and so it will keep recording while it's running. And so you can do trace command record and then -e trace point, trace, as you did with trace command start, to enable the trace points you want to look at, and it will dump this stuff into a file. It does that when you hit Control C at the end of the run, and it can collect huge amounts of information. Like I've multiple tens of gigabytes of data can be collected in this way. And once you've got the stuff into the capture file, the default capture file is trace.dat. You can then look at it with trace command report. And as I mentioned before, you've got filter options that you can use. You can specify which trace points you want to see, or you can pipe trace command report into a pager and use search in there, or you can pipe it into awk or grep to do any kind of filtering you might want to do. I find the -F option is more efficient than actually using awk or grep, but sometimes you really want to get a very particular output format, and so I use awk quite often to pull out very specific items in each trace event. And as I mentioned before, if you don't want to see the symbolic names of the like NFS errors, if you want to actually see the numbers, you can do -R, and that will actually show you the trace events in the raw format that they appear in the buffer. So it's all a bunch of hex numbers. Although the fields in the trace events are displayed in ASCII. I mean, it does that amount of parsing for you, but the actual data in the event is displayed in just hex. It's raw. So I did expect to put this slide deck up somewhere. So I've included some supplemental material if you want to go and look at more detailed explanations of particular operations that you can do with trace command. The man pages are pretty good. They're recent. They're up to date. I haven't found a lot of bugs in them in the sense that there are pieces, there are options that are mentioned that aren't there anymore. They're pretty good. They're maintained well. There's a bunch of information under documentation /trace that explains a little bit more of the nitty-gritty of how you implement trace points in the kernel. And then there's plenty of stuff on LWN. This one particular article, 410-200, is specifically about using trace command, but there are a bunch of other articles on using the sysfs trace interface that explain a lot of the features of the trace subsystem that I didn't go into detail here. The trace command source code is might be interesting to you. If it is, I put the GitHub destination for that here as the fourth bullet. Are there any questions before I move on into the demo? Okay, before I take down the slide.
I had a real quick
ahead.
question.
Hmm?
So far there's no trace points in LockD. Is there any plans to convert the print Ks in LockD, or does nobody really care about LockD anymore?
I think we should do that. I don't have any specific plans, but yeah, we should do that. As I said, I'm not really talking today about actually how we implement the trace points. There's a lot of detail. They're kind of difficult to wrangle. I can do another presentation on just how we've been structuring them and the files and the details about how to add one of these suckers or even a new subsystem. If that's interesting to people, we could do that. Otherwise, yeah, eventually we should get to LockD, but I haven't. I guess I've got some patches I've got some server-side trace points that I've been working on. We can talk about that offline, and I think I did include LockD in that. So yeah, if you have some specific thoughts about what needs to be traced, let's talk offline, and I'll go back and look at my Tracepoint patches and see what's in there, and or I can put them up on my kernel.org repo, and you can have a look there. Any other questions? Is there something that people wanted me to cover in this talk that I didn't? Okay. Let me see if I can switch over to a terminal session. Real quick here. Okay. Can people see that okay? Or does it look like an eye chart?
If you increase it a bit.
Yeah, that's going to be a little bit of a challenge. Okay, let me do it this way.
Probably Command Plus or something like this.
Is that better?
Yes, thanks.
I can see that pretty well.
Okay. So I started with a large terminal window because the trace events tend to be, they use all the way, they're long. And so when they start wrapping, they get a little more difficult to read. But unfortunately, we don't have high resolution here, so I can't show you the large screen.
Where is this being screen? All I'm seeing is Bruce and you. I'm in something I have to click to see that.
Yes. I don't know
Okay.
what your.
Okay. I'll keep looking then. Okay.
It should
click on the stream or something.
Yeah, you got to click on the stream.
Yeah, one of the tiles, the tile that says live stream or something like that.
Yeah.
Oh, okay. Watch live stream. Thank you.
All right.
Got it. Thank you.
Let me see. What was I going to do? Oh, okay. So let's start with the set of events that are available to view. So I'm not sure there's any real order to this list, but it does group the subsystem events together. So here we see all the RPC over RDMA events. The ones for the client side start with XPRT RDMA underscore. On the server side starts with SVC RDMA underscore. You can see some here that are underscore ERR. As I described, these are rare events that happen in a sort of a fatal or infrequent error. So these are probably safe to leave on most or all of the time, and they will come out very rarely. But these are events that should not happen kind of events. You can see some of the other subsystems that are available. RDMA, CMA, that's the connection manager in the RDMA. MMU, KVM events. Here we see the RPC GSS subsystem. It's separate from RPC. I just happen to have the GSS subsystem loaded on this kernel because I've got a key tab and some turbos. Here are the Sun RPC events. Here are these aren't labeled underscore ERR, unfortunately, but here's the prog unavailable error. But these are the ones that come out if your RPC bind fails. Can you see what I'm selecting? Yeah, okay.
Yes.
Here's XFS file system events. I'm going to go through these quickly. Zen DRM. So there's lots of stuff in here. You can actually enable system calls. Here are the SCED events I was talking about. They're for the actual kernel scheduler has a bunch of these. So notice that there aren't any NFS events in here, and that's because systemd helpfully unloaded the NFS module. So I need to now, if I do that, here's NFS. Now you can see all the NFS events. So you've got write back, you've got events that fire when setAttr is done and getAttr is done. Invalidate mapping, that's a particularly popular one. Let's see, NFS4. Oh, we didn't get any. I guess we need this. There we go. Yeah, there we go. So the module name, the kernel module is called NFS v4. I'd forgotten this. But the events are named NFS4. That's the subsystem. So you can see stuff in here like, when a renew happens, when a set client ID happens. And there are similar events on the server side. This is a client system that we're looking at right now. So those are named NFSD, yada, yada, yada. And if we add events for lockd, it would be, we'd create a lockd subsystem and call it these events lockd : something something. All right, so that's trace command list. Maybe not exciting. Let me see. What did I want? Okay. So let's have a look at what some of these might look like. So I'm going to do a trace command record and pull out all of the SunRPC events. Oh, I need sudo, sorry. So it's running this command server-g. That's, of course, the Connectathon General Suite. And it's just capturing all the events. Now, this piece at the end is what happens when trace command record exits. What it's doing is this is a 12-core system, so each CPU has its own trace buffer, and at the end, trace command record will combine these and merge them together into a single trace log, which we can now look at with trace command report. I don't believe this needs a sudo, but there. So now you see why I wanted to have a wide terminal. So let's see, RPC socket. So this is kind of interesting.
Isn't it?
What's that?
You still can make terminal wider, isn't it?
I can make it wider, but that will reduce the size of the font.
Yeah, right.
Oh, okay.
So socket connect, you get to see an event come out when the client tries to make a connection, a TCP socket connection. So you get to see the error return. You get to see what address and port it was going for, and synsent is the TCP state. So you get a socket state change event that comes out when the state change socket callback is invoked, and you get to see, the new TCP state. So, and then this one shows right where the socket goes from synsent to established right there. You see the event. So this is, if I wanted to filter this out, so for example, I would do it like this. I can do it can either grep for this, or I could do it like this. So this is a capture filter. It's only capturing It's only capturing RPC socket state change. And so you could leave this on for a very long time and you'd only get a handful of these events. So like in a production environment, you might leave this on if you're looking for weird socket behavior or network problems. You can turn on some of these, and these will show exactly when connections are established and when they're closed. Let's see, what else was I going to show? Okay, there's another one that's related. It's called XPRT ping. It's a trace event that is recorded when the kernel RPC client does a ping of the remote server to see if it's up. So it might do this right when it's connecting to see if the port is awake and active on the server. So here's 20,048, which is the mount protocol. Here's the NFS protocol 2049. So there's the ping. So it gives you the result of the ping. It says, yes, I was able to send a ping, an RPC null packet, and I got a response. I sent a packet. So and in this case, this is the local host. It's doing a AF local connection to var run RPC bind.sock.
Chuck, are those showing probes that are firing in the kernel or in mount.nfs?
So this information over here is what I think you're asking about. That is the command that is running.
Understood.
This is the CPU ID. That's what CPU it's running on. This is the timestamp. And this is a trace event in the kernel. So
Okay.
the kernel is doing this trace event on behalf of this command. This is not happening in the mount command. It's actually in the kernel.
Got it.
Okay.
Yep.
What else did I want to show? Okay. Here's another way you can use trace points. I added a trace point called RPC stats latency. So this is a trace point that fires when an RPC task finishes, and you get to see the XID, the program version procedure, and here the procedure is named. It's not a number, it's a name. Null is 0, of course. And then you get to see the 3 latency statistics that the RPC client keeps. So you get to see these numbers for each RPC. So waited for 41 microseconds in the backlog queue, for 146 for the round trip on the network, and then the total execute time for the RPC from RPC begin to task exit was 813 microseconds. So this gives you very fine-grained visibility into how long each of these RPCs takes, and you get one of these for every RPC that's run.
Hey, Chuck, how hard would it be to filter out just the RTTs that were more than, say, 10 milliseconds? Is that easy?
It'd be easy to do. I've never done it, so I can't give you an example here, but you can use a capture filter to specify the trace point, the field that you're looking at, and like a greater than, say, 20,000 microseconds. And so then the trace point would only be recorded if this field was exceptionally large. That might be interesting as something that you leave enabled all the time, and so you get some information about when these things take a long time.
So
Right.
I have a question. So here is one of the things which we are really struggling with. So can we somehow merge this with the TCP packet that we see when we get the ACK from TCP request and when we get the reply. To kind of really measure the time which request was on a server, excluding network round trip.
Well, let's see. There are some trace events in the TCP module. I'm not sure there's one exactly where you want to see it, but this is what you have to choose from today. And if you don't see what you want here, I mean, then you'd have to add one or build a K probe to do it.
Can't you match them up by the RPC XIDs? Like, you know, get the XID from the trace output and then search that XID in TCP in Wireshark or whatever. Yeah,
that's generally the way I've been doing it, because I'm pretty lazy and ham-handed and don't want to write code to do it. But that's why the XID is recorded in the trace events. So you can look at a trace event with an XID number in it, and it lines up it lines up exactly with. So for example, this has an XID that's displayed in the same order that you see it, in the same endian as you see it in the Wireshark. And so you can just cut and paste this XID if you want to take a look at that. And I don't know of a tool that will actually merge trace capture and a network capture. That would be kind of interesting. The timestamps are in different format for one thing. But maybe you could do it with a clever Python script that matched on XIDs. That's certainly something that's within the realm of possibilities. We just don't do it today.
It'd be interesting to look at that TCP probe event. It looks really generic, so it might have a lot of different data that it's logging that might kind of give Tigran kind of what he's looking for. I've never looked at the output of that probe. It's probably busy.
Which one were you looking at?
I thought it was called just TCP under probe. The first one, yeah. It's like, well, that's a pretty generic name for a probe.
Well, let's try it. Okay, so there you see the the trace event from the TCP subsystem interleaved with the RPC events. I haven't looked closely at this, but this might give you a lot of information about exactly what you're looking for.
Right.
I'll leave this as an exercise for you, Tigran.
Thank you. Because sometimes you hit only file system cache, and then there's no real network traffic or something internal, and then you start to struggle. So where's my packets?
Mm-hmm. Yeah, that's one of the problems with looking at RTTs. I know you were referring to the client side cache, but if you're hitting the server side cache, that RTT is going to be small. The distribution of RT latencies is binomial. It's split. So there's a short one when you hit in the server's cache, and there's a long one when you actually have to go to the server's disk, which makes it a little difficult to make any kind of decision about, is excuse me, is this a particularly bad RTT, or is it just one where the server had to do something? It had to do some heavy lifting. And of course,
that's why I was looking for corresponding TCP ACK or network package that you say, okay, it's hit the server, it's not a network.
Mm-hmm. Yeah, that's something someone can look into. I think that'd be an interesting way of using Tracepoints. It looks like I'm not giving Bill a lot of time here, so let me.
It's all right.
Yeah, I think I'll just make another couple of comments and then finish this up. I mentioned max graph depth before and function graph. I can just do that real quick. Let's see. So here I would do function graph, max graph depth, we'll say 3, and we want to look at XPRT Connect. Notice it's running a lot slower. The function graph plugin is significantly more resource intensive than some of the others, the regular Tracepoints. But the output is interesting. Okay, so here we go. Let's see. Good enough. So I've scrolled. Sorry, I'm coughing. I've scrolled to the side here so that we can see just the function graph output. So you can see here where it's called, what it is calling, and what those functions are calling. And then since I set a max graph depth, it doesn't go any further than this. It just turns off function graph. The function graph plugin after the max graph depth is reached. And it's nicely interleaved with the actual trace points. So you can see how the client is controlling flow, based on which function it's in. You might, add that to NFS 4 open or something like that, so you can see how it's walking through its state management and things like that when it's doing an open. All right, I was going to show how to deal with the trace buffer sizes, but we can do that some other time, and I can just hand this over to Bill.
All right. Thanks, Chuck.
There we go.
Let's see. All right, so I'm going to take kind of a similar approach to Chuck. I want to see my little dark blue screen.
I see it.
Okay. So, as some of you may remember, not too long ago, actually 2 years ago, I was working on a thing that we were calling Flight Data Recorder. And Flight Data Recorder, I've had to put that on hold for a while, but I'm bouncing back to it. So Flight Data Recorder is another tool that's based on ftrace, consuming ftrace probes. So a lot of what you heard from Chuck, you're going to kind of you hear the same thing from me. It's a different tooling. So what is a Flight Data Recorder, and why is it different from what Chuck just described? So the idea behind Flight Data Recorder, and if you remember my previous presentation, which I have a pointer to, it's really, as opposed to a command line driven thing, it's an always on diagnosability mechanism, right? So you don't have to interact manually with the system. It's not going to be acceptable in a customer environment. Instead, it's something that just always runs ideally, and it has an interesting set of probes that it always turns on. And so when the customer reports a problem, you can go back and look to see what ftrace data got logged. So it's vitally important to kind of have the right set of probes. This kind of both ftrace probes like this are ideal for subsystems where you have a very rich set of ftrace probes. And I have to give kudos to both Trond and to Chuck. They've spent a lot of ergs of energy adding ftrace probes both to NFS and SonRPC. And that is an ongoing effort. And so if others want to volunteer to put probes in LockD, I think that's a really cool idea. So, but we have a lot of good stuff there. And over time, what we learned is that it takes time to kind of zero in on exactly what kind of probes are useful and what kind of probes are not. In particular, Chuck's heard me use this term talking about FYI probes, which I see a lot of, but which aren't really very useful. It's the I'm here probe, right? It isn't actually logging anything very interesting other than I hit this piece of code. Maybe that's sometimes interesting, but maybe it's not. In general, we want to focus on exceptional conditions, errors, whatnot. Although that's not really a policy of the flight data recorder per se, right? That's a question of how what the probes are logging and when they're logging and what kind of log. So specifically, what is FDR? Again, it's a system D daemon, which does kind of the same things trace command wants to do as an async daemon. It enables a set of ftrace probes that are specified in a config file, right, that are kind of known to the daemon when it starts up. It captures the data and saves it to a file if that's what you want it to do. And it manages space consumption too. So it has circular buffering capabilities, somewhat like the capabilities that T-Shark and TCP dump have, right, to keep the amount of space being consumed from going completely out of control. So that's a quick overview of FDR. Any questions about that?
So what is FYI?
For your information.
Probes. Okay, good.
Yeah, it's a probe that's of very little value. Let me see how to turn off screen sharing here.
So I use the term control flow, which is a little less pejorative.
Well, yeah, but
because
your manager enjoyed the pejorative term, so
yeah.
I'm repeating it for his benefit.
So FYI is as Bill said, it's just a sort of a raised hand that says I got this far in the code. But when I'm talking about a control flow trace event, it's usually something like I got this far. So for example, I posted this particular send, or here's where I put the TCP frame on the network. So that's not an exceptional event. That's actually a common event. But it tells you I got this far. And so it records the timestamp of when that happens. It might record other information that tells you exactly which RPC it was. So I respectfully disagree with Bill that these are not valuable. I think they're not valuable if you're looking for hard errors, because that's not what that's not what a control flow event is about. It's about, is the code executing as you expect it to? So I'll hand it back to him.
Thank you for that, Chuck. So I switched over to a different screen share. I wanted to give you the flight data recorder. So this is Fedora. I have the flight data recorder installed here. It's a system control commands to see what's happening. The config files for this thing are kept in fdr.d. Let's go look at what's in there. I hate that. So we have config files, even though it might be these config files are specific to NFS when they are, but there's nothing about FDR itself that is specific. So we have a README here that documents the syntax. This will eventually become a man page at some point. And the package delivers some samples. So let's take a look at the config file. Yeah, stupid copyrights. So let me show you kind of the basic for this thing. We give ftrace has the idea of instances. And so a particular config file can create an instance, and it can use any name it wants. This could as easily be FOOPI as it is NFS. I just chose to call it NFS for obvious reasons. Chuck talked about mod probe. For the moment, I'm FDR can do mod probes. This is something I plan to get rid of. It'll be on my to-do list, and I'll talk about it more later. The general syntax of the probe enablements is shown right here. It's pretty straightforward. Same basic syntax as trace command. I wonder why I use slash instead of colon. And you notice again the NFS4, not NFS v4 stuff. So my sample config file has a bunch of probes, relative to NFS v4. There are probes for v3 and v2, I guess. Another thing I wanted to kind of show here is similar to trace command. I can mix and match probes in different subsystems if I want to. If I want to see scheduler events like this Chuck showed in conjunction with RPC events and NFS, I can do that right here, right? I'm not confined into one particular thing, right? So I can mix and match as I see fit. So that's what the config file looks like. Now you might wonder, I'll answer the question for Ben asked it, how do I enumerate the available probes, right? And obviously you could look at the probes are in there, but I'll show you, and Chuck showed you the trick with trace command. I didn't even know that one. And I'll show you another one in just a second. So that's what and then here's the last little bottom save too. If I want to save the output somewhere, which chances are I want to, then there's how to do it. And a value can be specified here at the end to control the rotations and the maximum size. So, and FDR is willing to in order to rotate the config files. The logs. So that's what it looks like. Don't want to modify anything. All right,
Bill, you're dropping out. You're dropping out just a little bit. Is anybody else hearing that?
I saw it with
yeah,
Chuck.
It sounds like kind of over-aggressive background noise elimination. So maybe like when you get a little softer, it cuts you off. So maybe if you just sit closer.
I'm pretty close, and I also talk pretty loud. So
okay. All right,
so
I can still mostly understand. It's okay.
Yeah, it's just dropping every third. So if I want to turn it on, I have the familiar syntax to do that. I guess it's actually, I can never remember these kinds. All right, so I've turned on FDR, system D service. It has its own little log file. I get to see daemon started and it's running and process IDs and all that mush. I read the config file. It tells me a few things about what it's on. So I mentioned enumerating probes. As I think Ben mentioned, Chuck mentioned, I can also look at what probes are available in the sysfs file system. So let me show that real quickly. You can also look at the code, obviously. So here's a list of all the probes that are in the NFS v4 kernel module and their names. So I can pick any of these. I can even pick all of them if I want. That's probably a bad idea. Some of these are going to be very noisy. Some of them are going to be less noisy. So let's see what actually happens if I do some NFS. So I've done a mount, so maybe I can remember the name of the, no, that's wrong. So var log, NFS.log. So you see kind of some of the same Chuck demonstrated. We kind of have the same RPC probes turned on, XPRT ping, RPC connect. We also start seeing some of the NFS probes, in particular exchange ID. We see the exchange ID probe firing several times. First one got minor version missing.
Question.
Question?
Is this the file? This was generated from the file you just showed us, the config file. You just showed us. These are all generated from that. Okay, just checking.
Yeah.
Thank you.
That's right. Yeah, this data was generated live. It's crazy as that sounds. So you can kind of see some of the things that happen. I don't have very many turned on, so after a mount, not going to see a lot new. So let's try running some tests. So this is regular old Connectathon basic. See if we got anything new. So I don't have any probes that turned on that generated any additional probe data, and the test didn't fail either, really. So I'm not sure I would expect to see. So let's go turn on some other probes and see what we get.
Before you go a little farther, I just want to emphasize the difference between trace command and FDR. Their purposes are different. FDR is meant to be something that's run as part of system operation. So you basically want to turn on just the trace points that will give you not a lot. They're high value. They don't generate a lot of traffic, but what they do provide is important information when you need to debug a problem, like a network problem. A trace command you would use if you're running something down and you need specific and possibly voluminous trace events. It's something that you use actively. FDR is something that runs in the background and it's more like the SAR daemon, if people are old enough to remember that. So I just thought I'd point that out.
Yeah, I skipped over some of the kind of architectural FDR, but
so FDR would probably be better used for just the underscore ERR probes, correct? Is that something that FDR would be good for? Thank you.
That's the idea. One of the things, just to back up a little bit on that point, one of the things that we want to try to get away from is, what's the first act of customer support is generally asking the customer to reproduce the problem with TCP dump turned on or some other debugging aid turned on, right? So, and you can imagine if in production environments or bugs where data corruption is involved, that's not actually something a customer in a production environment wants to do. They want you to have already collected the data somewhere and it just gets uploaded to support, and you immediately resolve any further reproduction. So that's kind of the angle. So let's try turning on some probes and see if we can get something interesting. So Chuck added a new probe. At least I thought I did, and I'm not. So let's turn it on and see if Chuck did good. So Chuck added a probe that fires. I guess as we're doing XDR decodes of the NFS v4 request. So let's turn that one on.
Just curious, what happens when you misspell a probe, which I'm going to do for sure? Does it stop all the probes, or error just that one?
It'll just error that one. I mean, as part of its setup process, it's going to go look at those files out there in /sys, and if it sees that you named a probe that isn't out there, then it just ignores it. And I think it prints a goofy warning. So yeah, but it doesn't just quit. But that could mean that you didn't get exactly what you want either.
So there's also an interesting case where you're running this on kernel versions that might not have a particular probe yet. So for example, you're going back and forth between 5.4 and 5.8, and the set of probes changes. So FDR is designed it's to be designed to be robust in that kind of situation where it will like show an error, but it will still run and it will collect data from the trace events that it can.
Yeah, and that's an interesting challenge. The FDR can run against a variety of kernels, but probes are changing continuously. So it's pretty much impossible to have something that works on all kernels, right? Things change over time. So what you're seeing here is something that's based on, the current upstream 5.11, whatever kernel Fedora 33 is based on. So, all right, so let's run that test again. We're going to get some more interesting output. So one of the things we see when we turn time is maybe it generated a little too much data, and this is a good example of kind of an abuse of XDR status. Unfortunately, as we all know, the NFS clients intentionally or not intentionally cause error conditions to be created that are just part of the normal operation of the system. So these complaints are a little melodramatic. So, Operation 15, looks like this one does not have a textual decoding. That's a lookup operation, and error -2 is eno. So the client is just kind of through it, actually causing a bunch of eno errors to occur on the wire. Those errors aren't reflected back to the application, but the FDR doesn't know it. It just turns on probes and tell you what's happened. But that's actually pretty easy to deal with too. So one of the things FDR can do is let you apply filters. That's the wrong one. So let me show you the filter syntax. So the filter syntax is actually defined itself. Let's give a fancy one since we're running a little bit long. So I don't want to see any of those. So let me put a filter in here that says, well, I only care about this probe if there's a non-zero error and it's not enoent on lookup, right? And again, FDR doesn't define the format of this. This is really an ftrace thing because FDR is going to feed this directly into ftrace. So let's try that again. Run the test again. And so the old log got cleared away when we started. Now, no output got produced. The initial output we saw was from a mount. This thing's already mounted. So no errors of interest occurred during that test run. So vaguely boring. So let's take a look at one more example that I just kind of ran into accidentally. So let's go take a look at this mount point. This is a holdover from the virtual bake-a-thon. Oh, well, this is kind of strange. So the ls command reports an error, operation not permitted, and then displays this. This is really sweet. You can probably kind of guess from the name of the SharePoint what went wrong, but let's see if FDR logging was of any value. So we see a couple of new operations show up here, and not too surprisingly, the server returned wrong sec, right? So we don't show the RPC access method here. By default, it's probably auth_sys. I guess we could look at it if we want auth_sys. And we see not unexpectedly, the client does secinfo to go collect up the allowed security flavors for that SharePoint. And that operation succeeded. So, it looks like the client did kind of the right things in terms of I got wrong sec and I tried to recover from it by issuing secinfo, and then nothing after that. So the problem here, it's not shown, is that this client's not even set up to do Kerberos. So Kerberos only SharePoint didn't produce very appealing results. Now, we could have gone and turned on probes in RPC-sec, GSS, and seen some of the activity in the upcalls from the client up to that daemon. But I'll leave that as an exercise to the reader. So any questions about the FDR demo?
I have a leading question.
Okay.
Can I use trace command and FDR at the same time?
You can, as I understand ftrace, you know, if a probe is being queried by multiple clients, it looks like ftrace picks one of them, maybe the first one it across, and delivers that probe to that particular user of that data. And so chances are that's not what you want to do. That isn't exactly what I want to have, because it actually means ftrace users could interfere with each other, I think. So it'd be an interesting enhancement to ftrace. All right.
So maybe pragmatic one, where from we get it?
Yeah, that's true. I don't want to deliver data to hundreds of consumers just because we were running trace command with the same probes in 10 different windows, that kind of stuff. So interesting set of trade-offs.
Question, is this going to be coming to a distro in the neighborhood sometime?
Funny you should ask that, Steve. Let me go on to my back to my little ASCII slides. All right, so as Steve just said, paraphrased, where do I get some tech? Well, I'm blaming Steve, but as I said, I've had this work for a while, so I need to work with Steve to get this included in Fedora, and then ultimately in some releases of RHEL if they deem it worthy. The source has been released to GitHub, so it's out there right now for people to play with. There's the URL of the repository. This was licensed under the Universal Permissive License, which is a very permissive license, definitely softer than GPL. And so I believe that's acceptable for inclusion in Fedora. So feel free to download, build, customize, enjoy. It's out there for use right now. Next steps, as I said, get this into Fedora. Ultimately, RHEL, it'll be in Oracle Linux too at some point, and any other distro that finds it worthy and appropriate. So next steps in terms of enhancements. For those of you who remember 2018, the time I want to eliminate the mod probe keyword. As Ben pointed out at that point, I can actually hook into modprobe.d so that I essentially have deferred probes, if you want to think about it that way. You can name a probe that doesn't yet exist, and when a kernel module gets loaded, then FDR gets informed about it, and it can go then enable the probe in the module that just got loaded. So that's pretty cool. I've prototyped that, and it seems to work as expected. So I'm going to try to move forward with that. Other feedback I've gotten from Chuck is what you saw is an ASCII data capture that's fairly heavyweight by comparison. And we saw that trace command knows how to do raw data captures that generate the human readable form as a post-processing step. So I'd like to take a look at doing that too. I haven't looked at it at all, other than to try to stare at trace command to see what it's doing. And then there's a pointer to the previous little ASCII slide deck that I presented at Bakeathon 2018, which has a lot more of the general background architectural view of what is first failure data capture, and why is this interesting above and beyond trace command. So that's all I had for today. Quick demo. Really. Any questions before we wrap up?
So I have one. So do you know, Bill, the overhead of running this on a production system? So this is what this is meant, right? Just to enable on a production system.
Yeah, I don't have a good feel for that. My anecdotal evidence for a small number of probes is it's very low overhead. And it definitely has to be a lot lower overhead than running T-Shark or TCP dump, right? The amount of data is being generated is much, much smaller. But I don't have any empirical of anything in particular.
Yeah,
Or maybe
I-
check now. So in general, traces, what the overhead over traces?
it's just a single conditional branch in most cases. Do not turn on function graph. That's something that's very heavyweight because there's a infrastructure that's part of every function call and return sequence in the kernel. So as you saw, the code runs a lot slower when you do that. But when you just enable a handful of traces that are just active and not generating a lot of data, then the overhead is almost non-existent. Because I mean, there's a conditional branch in the code whether the trace point is enabled or not. So the expense in that case simply comes from copying data into the trace log. And these are the buffers are per CPU, so there isn't going to be a substantial amount of contention generated by locking or anything like that. It's just going to generate a little extra memory bus traffic.
Yeah,
these are designed for production use, and of course your mileage may vary. So a wise system administrator would measure for him or herself before actually deploying it.
Yeah, Steve did a pretty interesting implementation to allow ftrace probes to be evaluated and fire and fill the buffer without taking any locks at all. He's got a write-up, I think, in his documentation about how that works. So lock over, not really an issue. Now, if the probe is enabled and the filter blocking it out, then at a minimum, the code has to marshal up the arguments and call into ftrace and then look at what those arguments are, apply the filter, and either take the data and put it in the buffer or, reject it and do nothing, right? But if you look at the implementation, Mac, Chuck might eventually show you one, and the macro setup for the arguments can be fairly heavy just to get into ftrace and go, oh, that probe's not enabled for that particular condition, right? So good questions. Yeah.
So
What's the size of the ring buffer?
I think it's sized based on certainly number of system. I don't remember the calculations off.
Yeah, it's dynamically sized. The buffer size is determined per CPU, and then it's multiplied by the number of CPUs. I was going to show you how to find out what it is for your system by default, and also how to update it, but that's in the man page. We didn't have time for that. It's just a trace command start, and I think it's like a -B or something like that will allow you to set the size in kilobytes of the buffer per CPU, and then trace command show -- buffer size will show you what it is. So like on the system that I was running my examples on, the buffer size I looked at this morning was something like 1400 kilobytes. So it's not that big, but you can make it bigger.
Yep. Other questions, comments?
Do you think this is ever something that we could install and run by default in distros, or is this always going to be something that we ask people to turn on if they're hitting an intermittent problem?
Well, I hope this is something that eventually we could just kind of turn on by default, and its overhead is low enough, and it just always collects a small, interesting set of trace points.
Right. I would go farther than saying hope. I would say that's exactly what I had in mind when I conceived of the idea of a flight data recorder. Is it's something that's unobtrusive enough that, as Bill said, allows us to do first failure data capture. It's running by default when the system is installed. So, what I didn't mention before is that these buffers are also available in a core dump. So, if the system core dumps and tracing is enabled, like FDR has enabled these trace points, then you can look in the trace buffers. I think there are there are crash macros that enable you to find the trace data, and then you can go back and get some idea of what was going on at the time. So
there's actually crash
intention,
extensions that let you access that stuff.
Yeah, the intention is that this will be running all the time eventually.
Yeah, I've used those.
I worry. I'm less worried about. Oh, go ahead.
No, that's it. Go ahead, Bruce.
Yeah, I'm less worried about the overhead, and that seems like a solvable problem if it's a problem, and more worried about the multiple consumer problem, because I think that there are probably. I mean, we may think of trace users as kernel hackers, but I think there's probably other tools that are using tracing under the covers, maybe PowerTop or Latency Top or those things. People might use without even realizing that they're using tracing, and we could get into trouble if some of those tools start mysteriously missing trace events. So, do we have any sort of vague eventual plan for dealing with that multiple consumer problem, or am I worrying too much?
I don't think you're worrying too much. I don't have a specific plan, but it's on my to-do list to see, what's the breadth of that problem and what are potential solutions. It would probably require changes to ftrace itself. So
I expect that's true. I also agree that it's not out of line to suggest that we need to consider this and address it possibly, but I don't know if it's our problem to address or whether we need to approach Steve and ask him, Mr. Rustet, to figure out a mechanism to allow us to do this. I mean, when we set out to do this, I'll be really quick. When we set out to do this, we set up the FDR tool to run its own buffer instance, and I just am learning now that that's not enough to prevent interference with other trace operations on the system. Go ahead, Scott.
That's exactly what I was going to ask. I was going to ask, what's the point of instances? I thought if that wasn't to isolate the trace users from each other. But you answered that.
And maybe instances become the basis of that longer-term solution, right?
So you think the right solution is a kernel? I guess my first impulse was to think that maybe the solution should just be to make all those other tools clients of FDR, but I don't know.
No,
that might be a big political fight, I guess.
Right. Yeah. I think the kernel
if you can
needs to
solve it in
sort
the
that
kernel.
out.
That sounds easy.
Yeah, that's what we'd like to see.
I think the kernel has to do something.
Here. Okay, great. I had one other very minor question, which is I might have asked before actually. The config file that lists all the trace points. Can we get a directory full of those? You know, a fdr.d directory that you can drop different config files into and assemble the configuration from them?
Yeah, the way I have that set up now in the GitHub repo has a sample that has all the ones you saw today. It doesn't enumerate every single one, but it could. I am vaguely concerned about keeping that in sync with ever-changing kernel modules as probes come and go. If the probe changes format, that doesn't matter, but if probes come and go, then that's a management problem.
It is.
What I was asking for was whether we could get something like
.d.
modprobe.d or
yeah, it already works.
We have an exports.d or something. So a place where we could drop a config file to add some additional trace points without having to fool with the existing configuration file.
Okay.
I thought it already worked that way.
No, awesome. Okay.
I have a suggestion. In your demo, you put that very XDR error, and then you put a filter on it.
Yep.
Is that part of the default? That filter, is that part of the default that comes out of your Git repo? That shows that's a nice way to document it.
Yeah, I think it is. I'd have to go. I mutilated that file so many times. But yeah, I think it's in that default config file and the GitHub repository because I wanted at least one example that showed.
Right. Okay. Good. Yeah. Perfect.
Yeah.
Perfect. Thank you.
All right.
Yeah, it is in there. I just looked at the samples in your Git file. So good.
All right. Well, that's all I had today. Thanks, folks. Chuck, any closing remarks?
Yeah, it's 12:30. I'm sorry that I ran way over. I was expecting only to have half hour of information. If there's any further discussion, we can start in the general chat room here on the Discord server, or we could create a topic channel that's specific to FDR or tracing, whatever people prefer. Please let me know if there's something that we missed today, or if you'd like a follow-on presentation about actually writing, adding subsystems and trace macros, because it's somewhat complicated, and I have some battle scars to show. Otherwise, definitely want to hear from you guys about where we should be adding trace points, or maybe if there's one that's obnoxious and needs to be removed, or if we need more information in any particular trace point.
I see something called bat record. Is this being recorded?
I think Ben worked very hard to set that up for us. Yes.
Fantastic. Nice job. Will that be disseminated somehow?
Yes, it will.
Perfect. Thank you.
Okay. Thank you,
That's
Chuck.
the
Thank you,
PTO.
Bill.
Thank you, guys. Yes, thank you very much.
Thanks, everyone.
Yeah.
Okay.
Cheers.
Bye.